Let's have a look at how inverse trig functions work when we're in a right triangle. So in a right triangle, so something like this. Let's say this is the right angle, and let's say that the angle we're talking about is this lower left one instead of the upper right one. That makes the bottom side the adjacent side, and the opposite side is over here on the right. And the hypotenuse is opposite the right angle, of course. So the trig functions in a right triangle are just ratios of sides. So just for example, sine of theta is the opposite side over the hypotenuse. And if we switch inputs and outputs here, what we find to switch to the inverse function, we find that inverse sine of the opposite side over the hypotenuse is equal to theta. Well, this is actually only true if the theta that we're talking about is in the restricted domain for sine, which is from minus pi over 2 to plus pi over 2. But in a right triangle, the two angles that aren't the right angles, so these two angles in the lower left and the upper right, they're always acute angles. We have 90 degrees taken up with the right angle. That leaves 90 degrees to split between the other two angles. And so both of these angles have to be between 0 and a right angle. So that means that they're always guaranteed to be in this restricted domain. And they're also guaranteed to be in the restricted domain of cosine and tangent. So all of the trickiness that showed up in the most important diagram involving restricted domains, if you're just in a right triangle, none of that turns out to be a worry because you're always in the restricted domain. So inverse sine of opposite over hypotenuse is theta. Inverse cosine of the adjacent side over the hypotenuse is theta. And of course, inverse tangent of the the opposite side over the adjacent side is theta. So in any particular situation, if you're trying to find one of the angles in a right triangle, which trig function you use just depends on which sides you have available to work with. Right? Each of these three ratios is different, so just use the trig function that matches up with the sides that you have. Of course, if you're in a right triangle and you know two sides, you could find the third side and then use any trig function, but you might as well save the work of using the Pythagorean theorem and just use the trig function that goes with the sides you already know. So let's look at a few examples. So first, let's find the angle theta in this right triangle. So in this setup, we know that this side 3 here, that's the side that is adjacent to our angle, and this side of length 4, that's the side opposite the right angle, and so that's the hypotenuse. We know the adjacent side and the hypotenuse, and so we should use inverse cosine. So inverse cosine of the adjacent side, 3, over the hypotenuse, 4, should give us our angle. So this input for inverse cosine isn't one of the nice ones, so we're going to have to use a calculator to approximate inverse cosine of 3 over 4. So punch this into a calculator, and if you're in radian mode, you'll get something like 0.841 radians. And if you are in degree mode, or if you convert that to degrees, you get something like 48.2 degrees. All right, so in this one, because we had the adjacent and the hypotenuse, the adjacent side and the hypotenuse, we used inverse cosine. All right, let's look at another example. Let's find this lower left angle in this right triangle. So here we know the opposite side, that's the side of length 1, and we know the side adjacent to the angle, that's length 5. We don't know the hypotenuse, so we should use a trig function involving the opposite and the adjacent side, and that would be tangent. So inverse tangent of the opposite side, which is 1, over the adjacent side, which is 5. All right, so inverse tangent of 1 over 5. Again, this is not one of the nice inputs for tangent, for inverse tangent, so we're going to have to approximate this with the calculator. Punch it into a calculator and you get something like 0.197 radians. Or if you want to use degrees, it's 11.3 degrees. All right. Finally, let's look at this one. Let's find the angle, the right-hand angle here, and this right triangle. So this time we know the side that's opposite the angle, and we know the side that's opposite the right angle, so that's the hypotenuse. And which trig function involves the opposite side and the hypotenuse? That's sine. So let's use inverse sine. So inverse sine of the opposite side, which is 6, over the hypotenuse, which is 7. And yet again, this is not a nice input for inverse sine, so use a calculator to approximate this, and you'll get 1.030 radians, or about 60.0 degrees. It's actually not exactly 60 degrees, but it's very, very close. So in right triangles, all of the inverse trig functions work out pretty much how you would expect, with the added bonus that you don't have to worry too much about domain because the angles involved are always between 0 and a right angle.